Last episode, you turned text into embeddings, dense vectors where closeness means meaning, but a vector by itself answers nothing. The whole point is retrieval. So here's the question. Given one query vector and 10,000 stored ones, how do you find the nearest few and find them fast enough that nobody waits? Start with the dumb version because it's also the correct one. To find the closest vector, you measure the distance from your query to every single stored vector and keep the smallest. That's brute force, and brute force is never wrong. It just gets slow when every single one is millions. FAISS is Facebook's library for doing exactly that, but fast. The simplest index it offers is index flat L2. Flat because it stores your vectors as is, L2 because it ranks them by squared Euclidean distance. It's still brute force under the hood, but it's brute force in tight C++ with SciMD. So the same scan that crawls in a Python loop finishes in milliseconds. The shape of the API is two verbs. You add your whole matrix of vectors once. That's the index built. Then you search with a batch of queries and a number k, and you get back two arrays, the distances to the k nearest, and the indices of which stored vectors those were. Indices, not the vectors themselves. FAISS hands you row numbers and you look up the rest. And you never trust a search engine you haven't tried to fool. The honest test is to plant a known vector in the index, then query something that is almost that vector. A whisper of noise added. If FAISS is real, it returns that planted row as the number one hit, at a distance just barely above 0. If it returned anything else, the index is lying. Here's the whole thing in one file. We make 10,000 random vectors in 128 dimensions, build an index flat L2, plant a marked vector at a known row, then query a noisy copy of it and confirm FASS finds the original first. Up top, we seed NumPy and generate the corpus, XB shape 10,000 by 128, cast to float to 2 because that's the only D-type FAISS accepts. Then the build is two lines. First, index flat L2D makes an empty index sized to the dimension, and index.add xb pours every vector in. We print index.total to prove all 10,000 landed. Now we set the trap. We pick row 42242, copy that exact vector out as our planted, and make the query by adding a tiny Gaussian nudge. Standard deviation 0.01, so the query is near the planted vector but not identical. That mimics real life. Your query is never byte for byte one of your documents, just close to one. The search itself is the single line everything else exists for, di conc index.search cosxq k with k equal to 5. I comes back as the 5 nearest row indices for our one query, sorted nearest first. D is the squared L2 distances in the same order. The first entry of each is the champion. 800 is the row FASS swears is closest. Run it. The index reports a total endor row of 10,000. The search finishes in a fraction of a millisecond, and the headline line prints the winning index 42242, the exact row we planted, with a top distance around 0.02, just the noise we added and nothing more. The assertion that i's row equals 4242 passes. The terminal and the card say the same thing. The figure's bar chart plots the fave returned distances rising left to right. The first bar a violet sliver near 0, labeled row 4242. The rest taller and unrelated. And that first bar's height equals the 0.002 printed in the terminal. The planted row came back first. The engine is honest. Brute force done in tight C++ gives you exact nearest neighbors in milliseconds, and a planted vector proves it never lies. Next episode we ask what happens when every single one is a billion vectors and a flat scan finally buckles. SH13 FAISS at scale at